Let's welcome our next speaker. So next up, we have toward practical lattice-based proof of knowledge from Hint MLWE. And our speaker will be Jordan Kim. Can you hear me? Oh. 1 second, we're just bringing up the. Sure. Okay, hello everyone. This is Jordan Kim from the class. Today we're going to talk about new framework and the lattice proof of knowledge. This is a joint work with Information University. The one, yeah. Okay, let's start with a slide background. So, proof of knowledge is basically a cryptographic protocol, which is to prove that I know some knowledge. So, to make it sense, then it needs several properties as following. So, the first one is properties, which means that if I really know the knowledge, then I should be able to pass the verification. And the soundness means soundness means that if this argument is a fake, then we should not be able to pass the verification. And this is very difficult properties. But if you want to make the protocol to be more useful, then we need an additional property which is called zero knowledge. And the purpose of the zero knowledge is to make that the verifier should not be able to learn any of the information of the knowledge that the paper has. And in this talk, we are going to mainly focus on the zero knowledge property. And of course, in our work as well. So to be more precise, we are more interested in the lattice and zero knowledge property in lattice-based proof of knowledge. And many of the proof of knowledge, lattice-based proof of knowledge systems are working on the linear system. So the high-level description is as follows. So the public values we have are like the matrix B and the vector C. And what we want to prove is that we know the knowledge of this small vector R and some encoded message vector, encoded vector M, which satisfy the relation that C equals to the R plus N. And we can actually find a lot of examples that satisfy this relation, but let me give you some of the examples. So first example is the VFB encryption. So basically, VFB is the ring LWE based fully homomorphic encryption scheme, but it can be also regarded as a standard ring LWE public. So the public key of the VFB encryption consists of a pair of the polynomials, and the ciphertext is generated as follows. So we multiply by a small polynomial R2, and then add a small error vector R0, R1, and then lastly we add the encoded message 2/t times 3. So this formula can be a bit complicated, but it can be also expressed as C equals to BR plus M formula if we define B equals to the concatenation of the identity matrix and T and the vector M to be as follows. So when we think of the proof of knowledge for C equals to BR plus M relation in VFB encryption, then it can be regarded as proof of plaintext knowledge. And the goal is to prove the knowledge of the message and the encryption randomness R for given ciphertext C. Another example is VDLOP commitment. And actually, this example is much simpler because the commitment procedure is exactly just C equals to BR plus M. And the proof of knowledge for C equals to BR plus M for VDLOP commitment is actually called proof of open knowledge. And this is to prove the knowledge of the message M and the commitment randomness R for given commitment C. So as you can see in both of the examples, we are dealing with both of the message M and the randomness R. So actually, what is the motivation of this work? The motivation of this work can be actually phrased as zero knowledge over T. So when you think of the conventional goal of the zero knowledge, then you can think of that, we always target the zero knowledge for both of the massive and the randomness part. But the zero knowledge of the randomness can be an overkill for many of the proof of knowledge applications. So the thing is, randomness is actually an auxiliary image for the encryption or commitment to protect the message. Right? So actually, the randomness is not a primary goal for the problem. So in this perspective, then we can have the following natural question. So how about refining the goal of the zero knowledge? So how about we just target the zero knowledge only for the message? In other words, can we still achieve the zero knowledge of the message, even if we allow the information leakage for the randomness? So to understand this motivation a bit more precisely, let's look into the previous approach and let's look into how to have it done. So previous approach usually use the typical sigma protocol to prove the C equals to BR plus M equation. So Kruger has an input M and R, and he wants to prove that I know M and R when the C is given, which holds C equals to BR plus M. So the first procedure is to send a commitment of random values, which is denoted by BI, and then receive the challenges gamma I from the verifier. After that, Cooper gives a response to, back to the verifier, VI comma ZI, which is actually the linear combination of the values that Cooper already has with the challenge given from the verifier. So because we are now focusing on the zero knowledge proof, what we really need to be interested in is this response part. So because as you can see, the response VI comma ZI actually contains a partial information of the M and R, which are the target of this right. So for the zero knowledge proof, the previous work adopted several statistical methods, and one of them is noise splitting. The noise splitting technique means that we set this masking vector UI comma yi to be exponentially larger than M. So the purpose is to make the response VI comma ZI to be statistically independent to M comma R. Then it directly implies the zero knowledge of M and R because there's no information of M and R from the transfer. So this method is very simple and strong, right? But the fundamental drawback of this method is that it inherently accompanies the exponential overhead. So another statistical method is rejection sampling. Actually, this method is most widely used method for most of the lattice-based proof of knowledge systems. And the way they do is we restrict and rerun the whole steps of this procedure with certain probability. So the method is different, but the goal is the same. So the goal is the same to make the response VI comma ZI to be statistically close to independent to M comma R. So this also directly implies the zero knowledge of M and R. So compared to the noise splitting technique, then it does not have any exponential factor. So it even can achieve the constant overhead, but still it requires multiple iteration of the whole steps. And this number of iteration can be exponential in certain cases, like a multi-prover probability case. And also in certain conditions, rejection sampling can be vulnerable. So from this old observation, we wanted to make a kind of new thing under the refined zero knowledge property. Refined zero knowledge property means zero knowledge only for message. And because we are now targeting a weaker version of the zero knowledge, we might be able to substitute this old statistical method by some more efficient computational hardness. So yeah, in other words, we can say that even if our goal can be said that even if the randomness information is partially linked from the response ZI part, we might be able to achieve the perfect zero knowledge for a message, even under the computational hardness. So this is our motivation, and we exactly did this now. So we propose a secure lattice-based proof of knowledge protocol with refined zero knowledge, even without statistical method. And this refined zero knowledge property actually falls under the computational hardness assumption, which is called int NLW. When compared to the noise pollution technique, our method does not have exponential factor. And even when we compare to projection sampling method, we don't have the security dimension factor in the sampling stack. So and even we don't need any repetition. So we instantiated our new framework to the following primitives, which are actually introduced as an example in the previous slides. So the first one is proof of plain text knowledge over the BFP integration, and the second one is proof of open knowledge for video LLP. And we would like to note that the proof of open knowledge for video LLP, this work can be naturally extendable to various VLP-based ZKPF. And the last one we would like to emphasize is that we also constructed a very tight introduction from standard MLWE to int MLWE under the discrete box. Okay, so in the rest of time, let me explain the proof sketch of the zero knowledge only for massive. So when we look into the protocol again, then what we really need to show is that the transcript, which is the public values during the interaction, the transcript should not reveal any partial information of the message. That is our point. So to do this, what we prove is that the transcript is actually simulatable even without the message. So our first observation is that actually the transcript is consists of several components, but there actually exists several trivially simulatable components. So first, like for example, VI actually can be computed by the other components, and VI is also trivially simulatable for each case with some different risks. So I'll not explain the details, but the point is we can just forget about VI and VI part, and then just target to simulate the remaining components, C, gamma, and Z. And the second observation is that actually we just list out the public and the remaining components and look into that. So when we look into the tuple, the public key B and the remaining components C and ZI, then we can re-express this tuple as the following. To make it more clear, we can use a different expression of B, like B equals to R times I combination A. Then now the last tuple in this form is very clear for us. We already know what it is, right? So when we look into the first two components, then it is exactly the MLWE instance over the secret R. And because R is the secret, the remaining components can be regarded as the units in this secret. So following the philosophy of the MLWE assumption, if we can prove that these two tuples are computationally indistinguishable, then actually the proof can be just done because the second tuple, the last tuple, is actually simulatable without message. So this all observation brings us from the very complicated ZKP problem into very simple computational decision problem, which we call int MLWE. So when we think of the standard MLWE assumption first, then it is just this implies that it is hard to distinguish between the MLWE instance, which is of the form A, IA times R, with the random elements. The hint MLWE is just implying that even if we additionally publish several hints on the secret, the MLWE instance is still computationally hard to distinguish with the random elements. So if we can prove the hardness of this hint MLWE problem, if we have this assumption, then the last part of the ZKP in the previous slide is directly done. So the only remaining question is, so how hard this hint MLWE problem is. So how hard it is compared to the standard MLWE. And this theorem gives the answer. So we prove that there exists a polynomial time reduction from the standard MLWE to hint MLWE. And still, we preserve a lot of most of the parameters, only except the width parameter of the Gaussian canvas. And so what is the implication of this theorem? Because theorem itself does not imply anything, right? But so let's think of the very simple case. Let's set sigma 1 equals to 2 sigma, and sigma 2 equals to 2 square root b times sigma. Then you can easily check the condition of this theorem, highlighted as a red color. This holds. So you can easily check this. So then let's think about what these two equations means. So the first equation means that we just need to set the secret vector R of the hint MLWE to be one bit larger than the secret vector of the standard index. And then the second condition means that the masking vector yi should be just a square root L times larger than the secret. So under this condition, we can say that the hint MLWE problem is at least as hard as the standard MLWE problem. So if the time allows, I wanted to explain the details of the proof, but because of lack of time, we would like to at least give some high-level overview of the proof of this theorem. So because we are making the reduction from the standard MLWE to hint MLWE, we want to transform the given MLWE instance into hint MLWE instance. Then the hardest challenge would be how to generate the hints, right? So actually, it is almost impossible to generate hints from the A, AX plus E, but because all the elements are actually the random variable, what we can do is we can reverse the point of view by analyzing the conditional distribution of R for given hints, gamma I times R plus yi. So this conditional distribution analysis implies that even if we sample the hints first and then try to generate the second component of the hint MLWE, this I concatenation A times R, it is possible. Of course, it is possible under the discrete Gaussian setting because, you know, discrete Gaussian always have a bunch of the good properties. So for the whole of the detail for the proof, then please refer to our paper. I'm sorry. And okay, let's move on to the result part. So when we compare our new method to the previous method, then it can be just summarized as this table. So for a zero knowledge proof in the lattice-based proof of knowledge, the previous work always use noise flooding or rejection sampling, which are both statistical. Sorry, and they all targeted the zero knowledge for both message and randomness. On the other hand, our method is using a cryptographic hardness assumption called hint MLWE, which even has a reduction from the standard MLWE. And when we compare the soundness lag, then you can check that the soundness lag is much smaller than previous results. So noise flooding contains some exponential factor, and rejection sampling is actually the soundness lag becomes very smaller, but still it contains some dimension-related factor, square root dimension. But in our case, the soundness lag is independent to dimension, and this square root L, the L is just the number of chopping. And not just for the BFV encryption and the BDL commitment, we also applied our hint MLWE framework for more advanced ZKP proof systems. So, for example, proof of multiplicative relation and proof of knowledge for a Bernoulli solution for the linear equation over the finite field. So, from the rigorous analysis on the parameter selection, we proved that we can choose smaller dimension-related parameters than the previous results based on the rejection sampling. And so we didn't include the whole proofs in our published version. So if you're interested in the proof details, then please refer to our full version of the paper. Okay, this is all. Thank you for listening.
Okay, we have time for questions. Yes. Any questions? Yep.
Thank you for the talk. I'm just wondering if you could talk a little bit more about the intuition behind being able to leak this randomness and how much you're leaking to the version.
Oh yeah, that's a really good question. So maybe we can refer to this theory. So how much we leak for the randomness is related to this reduction. So as you can see, our hint MLWE assumption is based on the standard MLWE with a bit different standard deviation, right? So the gap of the standard deviation sigma and sigma 1, this can be regarded as how large amount we leak for the randomness.
Thank you.
Okay, thank you.
Thanks. How do you square the purpose reduction with some of the computational results around already equal to scale the security of the particular instance, at least the destination?
So Uh, are you talking about the concrete security?
Yeah.
Okay. So actually the concrete security, because we have reduction, right? So the concrete security of the hint MLWE is just relying on the concrete security of underlying standard MLWE. So we can just measure the concrete security from this all the parameters and the sigma.
Okay, any other questions? Let's thank our speaker. Thank you very much.
Okay, thank you.
Okay, we have one more talk in this session. Okay. Yeah. Waiting for the speech. Yes. That's good. Okay. Okay, let's get started. So next up we have publicly verifiable zero knowledge and post-quantum signatures from Rolla in the Head. This is a paper by Carsten Baum, Stephen Dufek, and Hem, Michael Plus, and Mimi Rossini, Lawrence Roy, Peter Scholl. Our speaker will be Michael Plus. There's a button, maybe flip the button.
Yes. Better? Can you hear me now?
Thanks.
Good. So better now?
Yeah.
Thanks. So the slides also unfortunately. Thanks.
So first, let's recall what zero knowledge proof of knowledge are. So I guess you know, but we have this prover and verifier, and we're considering some NP relation R. And the prover and verifier have as input a statement X. And the prover also gets a witness as additional input and wants to prove that in our setting that it knows this witness. This is the knowledge soundness property of the protocol. But we also want zero knowledge, so the prover should, the verifier should learn nothing but this statement, so that the prover knows of this statement. And this is a very useful primitive, both in theory and practice, and there's been a lot of research in many directions in zero knowledge proofs. And like here's a very simplified overview with only two axes we'll consider. So proof size of zero knowledge proof systems and like prover runtime. And on the top left, we have like linear size zero knowledge proof systems, which have rather fast provers. And so there are MPC in the head and the volley-based zero knowledge as examples. And we also saw like the lattice-based proof systems, which probably also belong here somewhere. And then there are these succinct proof systems where the proofs are actually smaller than the witness, but where the prover runtime is usually much larger than for these linear size protocols. And what we are looking at in this talk are volley-based zero knowledge proof systems. So these are usually interactive. So we have a designated verifier setting, and they are linear size with rather small factors. So they are interesting from an efficiency perspective. And let me take our results kind of ahead. So what we will do is we will do volley in the head, kind of like MPC in the head. And we have nice characteristics for this approach. It will be fast. We will only need symmetric primitives for this. It will be rather simple and flexible because we can reuse the volley techniques for zero knowledge protocols. It will be secure in the random oracle model. And as I said, it will also be linear. So I've already talked about these volleys. And now let me kind of first explain how volley-based zero knowledge is actually done. So for this, we need this vector oblivious linear evaluation functionality, which is kind of a arithmetic type of oblivious transfer. So we have a vector of u and v over some field, which the prover or for the volley, the sender inputs into the volley. The receiver for the volley, in our case, the verifier, inputs some scalar and then receives from the functionality this q, which is just the linear combination u plus delta v. And what we actually use or realize in our protocols often is random volley instead. And like random OT, you can de-randomize volleys to get chosen volleys. So the random volley instance, we just choose u, v, and delta randomly and give them to the prover and verifier respectively. So how do you construct zero knowledge from these volleys? You go through linear commitments first. And how do we get a linear commitment from volleys? Well, this is almost immediate. So we choose as the VIs the message we want to commit and choose the UIs as masking randomness. And then basically the QIs along with the delta will be the commitment. And this is hiding because, well, these UI terms are chosen uniformly at random. So they perfectly mask the VI term. This is binding because if you look at the volley equation, if you could open some QI to two different values, then just by using the linearity of the equation, you will see that you must have guessed delta. And if the verifier uses a high entropy delta, then this should not happen. So finally, why are these commitments linear? Well, you can just sum two commitments together, and then you can see, well, the equation was linear to begin with, so we do get our linear commitment schemes. And now from linear commitment schemes to zero knowledge, this is fairly generic. So the usual approach is commit and proof. So let's consider the relation of quadratic equations because this is NP complete. And what you would do is you would first just commit to the variable assignment, which is kind of satisfying for the set of quadratic equations. And then you can, well, any linear equations you can trivially check just by using the linearity of the commitment. Now, for quadratic equations, you cannot check them immediately, but there are linearization techniques, and I will show one in the next slide. So this is also kind of easy. And more concretely, in our setting, we often want to verify very specific, like circuit satisfiability statements. And these can actually be treated like more specifically by doing the proof and verification kind of gate by gate. That is, you commit to the inputs, and then for every multiplication gate, you also commit to the output. And for addition gates, you do not need an extra commitment because we have linear commitments. You can just compute the addition on the commitments. And then in the end, you have to also prove these quadratic relations for the multiplication gates. So now let me explain how we do the quadratic equation check. So let's first recall that the prover holds these UI, VI, and the VIs are the witnesses in our case, or witness components. The QIs are commitments, and we have this volume relation. So the prover wants to prove now just this one quadratic equation, f of v1 to vn should be 0. And we will just write this equation down, but for the commitments instead, and see what happens. So we have this f of q1 to the qn. This equals this thing, and now we can expand this to actually like a quadratic relation in delta. So we see that the first term is just f evaluated at u1 to un. The second term is some other garbage term, which only depends on u and v, and this is our linear coefficient. And finally, here as quadratic coefficient appears f of v1 to vn, and this should be 0. So if the prover is honest, if the statement is true, then this expression is a linear expression in delta. So the idea to linearize our quadratic equation is to have the prover just send these a0 and a1, which only depends on u and v, so the prover can compute them and can send them to the verifier. And then the verifier will do the check with delta, which the verifier knows. The prover does not know delta, so this gives us the security. Now, as explained, this would not be zero knowledge because here A1 obviously depends on the witness, and this is kind of bad. But since we just need to be sure that this relation is a linear relation, we can just mask A0 and 1 by random terms. And this costs us like 2 extra commitments, and that's it. So let's look at the cost for these types of zero knowledge proofs. So we saw that for zero knowledge, we need some extra commitments to masks. If we want to prove more than one quadratic equation, we don't have to repeat this protocol many times. Instead, we can just use a linear random combination of the quadratic equations. And if one of the equations would be false, then with high probability, the linear combination would be false. So we reduce the check of the whole set to just a single check. Now we can also do for larger equations than just quadratic, if that's useful, by extending this check. But let's stay with quadratic equations here. And we saw that now in total for circuit set, we have commitments to the inputs. For every multiplication, we need one Doli for, well, the additional variable we need to commit to. And in the end, we need openings and a few volleys for the zero knowledge part. And that's it. So this is how these volley-based zero knowledge protocols work on IM. And now let's try to make these volley-based zero knowledge non-interactive. And we do this by doing volley in the hand. So for this, we need to go from the private coin setting, where we kind of use some very efficient, let's say, LPN-based volley to some public coin realization. And the idea here is that the delta, which the verifier chooses, does actually not have to be secret at the end of the protocol, because it's not really a secret of the verifier, which, yeah, kind of, it's just a temporary secret for the protocol to ensure the sound. But you don't need to have the guarantee which the volley functionality gives you, that the prover will never learn this delta. And so our idea is that we kind of commit to the volley, and in the end, let the verifier just send delta in the plain text, and the prover kind of decommits to the volley. And what we actually do is we commit to OT values and use the transformation from soft spoken OT to kind of transform an all but one OT into a volley. And this idea, like for 1 out of 2 OT, is not entirely new. So there's prior work which used this, but the context is kind of different. We're trying to do the volley in the half, and this was for VOC secure protocols. And this, I give a high-level overview of the whole pipeline of our approach. So we have here some volley-based zero knowledge, which is in a volley hybrid model. We need some extra properties because if the protocol would be inherently private coin, we can of course not make it public coin. So we need to assume that this protocol is public coin to begin with. Then we need some way to realize the volley using an all but one OT. And for this, we will use the soft-spoken OT protocol. And then we now have a protocol, zero knowledge protocol in the all but one OT setting. And our compiler can basically take such a protocol and replace the OT by a vector commitment. And this is the high-level idea for the interactive setting. For the non-interactive setting, we can now apply the Fiat timing transformation if everything is public coin, and we get a NISM. For this, we also need some round-by-round counters so that this is secure after the Fiat timing transformation. And now let's take a brief look at all of these building blocks. So first, we have the vector commitment. The vector commitment is based on these PRGs, the GTM tree. So what we do realize here is just a random vector commitment. So because we will also just realize a random volley or random OT. And we can get this by inputting here some randomness, and then we go down the tree, and now we get many random seeds. And what we would like to just use these seeds as our random messages. We cannot do this for technical reasons. So we apply another PRG with some special properties, which then gives us our message and a commitment to the message. Now we do hash these commitments together to actually get our vector commitment in the end. So the vector commitment is just this. To open the vector commitment at all but one index, let's say at every index except for 0, 1, we can then just take the copath, the seeds on the copath, and hand them out, and also like commitment here. And this gives us now a communication trade-off because the larger the tree, the more we need to compute, but the smaller the opening is relative to the number of commitments. Now with this vector commitment, we can realize we need to instantiate the volley. For the volley, we use, as I said before, the soft-spoken volley transformation from all but one OT to volley, and we get an volley over Fn. Now, due to this communication trade-off, n has to be Pauli. So our delta would also be only Pauli. This means this is not secure enough for our purpose. So what we need to do is we need to kind of repeat things in parallel. And then we have to decide on how to repeat exactly. So how do we kind of insert the witness in the repetition, repetitions, parallel repetitions, and a simple way is to just, well, do a repetition code, basically. Or more generally, we can use any kind of linear code and get some subspace volley out of this. So with this, we now have to realize the zero knowledge protocol, given the volleys. And there we actually provide two protocols. So if we work over a small field, small time field, then this is nicer for this soft-spoken OT conversion. And it makes sense to use the repetition code because then we can easily work in an extension field. And this Quicksilver-based zero knowledge protocol, which I showed in the beginning, of this quadratic equality check, works very well. And we can work easily over these extension fields, which is very convenient. If Q is just arbitrary and say some big prime, then we need to use different techniques, and we would use a general linear code instead. So let me just note here that one of the difficulties is that these delta i's are now uniform from a subset of the whole field. And this needs modifications in the security proof for the zero knowledge, or the construction of the zero knowledge, and like the soft-spoken OT security proof also needs adaptations to kind of handle this case. And with this, let me demonstrate our volley in the head and one example. So face a post-quantum signature from AES and volley in the head. And here the idea is to just use a standard template. So what we do is we prove knowledge of a secret key, so that for the verification key, which is just X and an AES encryption of X, under our secret key, that we do know this secret key. And by the PHM transformation, we can get from such a proof of knowledge a signature scheme. Now, for this, we do have to handle AES in a zero knowledge proof. And how do we do this? Well, we can actually see that for our protocol, AES is kind of arithmetization friendly, because AES is F2 linear. And if we just choose a prime as 2 and use a repetition code, this actually works quite well. Now, we also have this S box, which is basically inversion in F2 to the 8. And F2 to the 8 is an extension field. So this also works quite well in our setting. And as you can see, we do not need too big of a witness. So we have a 1600-bit witness, and we need 200 quadratic equations to prove this, this in constraints. And like in concrete numbers, this translates to a signature scheme, which in its small instantiation for 128-bit security needs 8 milliseconds for an optimized implementation to sign and verify. So sign and verify is basically identical in efficiency here. And we have a 5 kilobyte proof size. Now, if we trade off in this vector commitment, the size for like speed, then we can get down to 1 millisecond, but our signature size does increase to 6.3 kilobytes. Here are also the parameters for 256-bit security. And let me just say that this scales roughly quadratically in the security parameter, and you can see. And with that, we conclude. I hope I could convince you that like volley-based zero knowledge is a type of lightweight, fast, and linear-sized zero knowledge proof system, and we can make it publicly verifiable or public coin, and we can get NISX from it using volley in the head. And finally, we have a conservative, in the sense of based on AES, and reasonably performant signature scheme from this volley in the head paradigm. Yeah. Thank you.
Okay, we have time for questions. And also, anyone listening online can ask in the chat. No questions? Okay, maybe I'll ask quick questions. So, I mean, where do you see this going? Maybe for future work.
Yes, so there are quite some questions here. Like I said, we have this question with these guys here. So it seems that you can optimize the performance a bit more here. There's also the big question of these LPN-based volley constructions, which are very efficient, especially size, and we cannot use them at the moment. So we use probably different techniques. I think these are like.
We have a question.
Yeah, thanks for the talk. Just a question regarding, let's say I wanted to use your volley in the head as like my snark or whatever. Do you think, I'm assuming it seems it's faster than other like medium type snarks that are out there now, but you have a larger proof size. So do you have scenarios where you would value that speed up over the linear size proofs versus like breakdown or combined chips? Linear size proofs would be better. Probably most of distance.
Yeah. You want some scenarios with these hours?
Yeah. Besides what you.
Yeah. So I think like many of these more interactive privacy preserving protocols just need a quick proof, and then size is not that important. Like for anonymous credentials, I don't think it benefit much if your size is tiny, but you have to verify for a long time or prove for a long time, especially if it should run on your smartphone. Where kind of the prover is the thing which should be fast and not the verifier. So it's not just like on this trade-off line have also this succinct verification, which you do not achieve.
We have another quick question here.
Yes, I just want to ask, is this technique also useful for volley-based ZK that is beyond just multiplication and addition gates?
What do you mean? Volley-based?
Says you use volley-based ZK to prove some permutations.
Permutation. I don't know. I think you would just try to use like volley-based permutation proofs. Don't know if there are like special types of proofs.
Sorry, thank you. We have a question from online. So, how does the computational cost compare to Sphinx, the NIST solution?
Oh, yeah, I did not put the numbers here. I think like the prover is a bit, and if parameters get large, significantly faster, at least in the fast instance, and for large parameters, even in the small instance than Sphinx. But the verifier for Sphinx is faster than the prover or the signer. So in that sense, there is a trade-off. I think for the fast instance of Space, we kind of get to the performance of Sphinx. So the Sphinx verifier, so sometimes we have much faster signing time then, while having a similarly sized proof. Whereas in the small instance, like verification would take longer, but our signatures are kind of significantly smaller.
Okay, well, let's thank our speaker. And now it is actually a coffee break.